Okay. Okay. So thank you very much for joining the UNIFI seminar series. This is our last one for spring of 2022. We'll start back up in the fall. Today, I wanted to introduce Jack Flicker, who is a principal member of the technical staff from SANDIA National Laboratories. He will be speaking today on hardware in the loop evaluation of grid forming inverters. So I'm going to turn it over to Jack. If you can go ahead and share your screen and come off mute, and then we'll go ahead and get started. Okay, I think we have you now.
Okay, yes, you have me. Sorry about that.
Yep, no problem.
Okay. Okay, can you see my screen? Hear me all right?
Yep, we're all
Okay.
set. Go ahead, Jack.
Okay. So hi, everyone. My name is Jack Flicker from SANDIA National Labs, and today I am going to talk about some of the work that we've been doing here at SANDIA on evaluating grid forming inverters in hardware in the loop, and specifically in power hardware in the loop. So a lot of this work from various different projects have been funded by DOE and have been done by either myself or my co-authors that are listed here in a variety of different projects. So for those of you not familiar with SANDIA, we are a National Nuclear Safety Administration lab, or an NNSA lab, that had its start as part of the Manhattan Project during World War II. So we were the engineering portion of the Manhattan Project with our sister lab, Los Alamos. But after the war ended, SANDIA was established by Truman as a national security lab in order to, quote unquote, render exceptional service in the national interest, which means that we have a changing mission portfolio as national security priorities change for the United States throughout the years. And there's a very long, very, very interesting history of how national security priorities have changed over those years. But we currently have 5 major program areas, which you can see here on the right. SANDIA is the largest national lab. We're located in beautiful Albuquerque, New Mexico. And we have satellite sites in California, Nevada, Hawaii, Alaska, and elsewhere. We have about 15,000 employees and an operating budget. It's a little under $4.5 billion. So you might be asking yourself, why is a national security lab, especially one that's part of the nuclear weapons complex, doing work with the electrical grid and grid forming inverters? And really, it comes down to the fact that our mission has always been national security. So around the end of the 1970s, with the oil embargo and the energy crisis, there was a general recognition that energy security, surety, and resilience were key aspects to national security. So as you can see by the green icon on the lower right here, energy is one of the 5 key mission areas for SANDIA National Labs. So SANDIA has been carrying out grid modernization research since like the late 1970s, starting with the Distributed Energy Technology Laboratory, which is where I do all my work. In the early days, we were mostly focused on evaluating PV panel performance and reliability, and this generally transformed into PV inverter and interconnection work, and includes helping to evaluate 1547 testing protocols, arc and ground fault protections, and just generalized inverter reliability. In the 2000s and 2010s, we transitioned to a number of different areas: civilian, military, microgrid planning, microgrid operations, grid resilience, and power electronics are just a few of those different areas. But the main facility where we evaluate our hybrid systems is the Distributed Energy Technology Lab, where we have both real and simulated PV and energy storage. We have grid simulators, we have a number of single-phase and 3-phase inverters, a diesel genset, cybersecurity evaluation equipment, and thermal chambers. And we also have the ability to evaluate these devices interconnected with the real simulated grid, with the real grid, island into a microgrid, or coupled into a hardware in the loop evaluation. So today I'm going to highlight some of the work that we've done in evaluating grid forming inverters and hardware in the loop, or HIL. I mentioned HIL a few times, but I'll give a general overview just so we're on the same page. So whenever we're thinking about evaluating a technology or a concept, there are a number of tools you could use, and there tends to be this natural trade-off between how flexible the tool is or how tractable it is to implement in different conditions versus the fidelity or how much we can trust those results to mimic what we might expect if we were actually put that technology into a specific condition. So in this continuum, on the very, very highly flexible side on the left, we have things like pure simulation, where we have this extended system representation where aspects of the system have been totally abstracted to some model. It's highly flexible in that we can do scenarios that we couldn't implement in the real system, but we have to be very careful because since we're abstracting behavior of the assets, which tend to be highly nonlinear in reality, it can really deviate substantially from real life if we don't fully capture all the nuances of those non-idealities. On the other end of the continuum, we have pure hardware. Hardware is really, really highly accurate in capturing all these minute nonlinear actions. Since we have that physical asset in the lab, and we don't necessarily have to do any model or any abstracting or anything. We actually have that device. It's physically connected to another device. However, as any experimentalist can tell you, when we do hardware, we tend to be relatively limited in the flexibility of our experiments because we can't always put every scenario in. It can get really intractable in time, money, and space, and it's even possible at all to replicate the variety of experiments that are being done on the simulation side. So squarely in the middle of this regime, kind of the moderate flexibility and moderate fidelity, we have this hardware in the loop, or HIL. And in hardware in the loop, we're coupling real hardware into a system that's simulated. And the key here is that you have this feedback between the two, between the hardware and the simulation in a closed loop mechanism. So that the measurements taken on the real hardware in the lab are represented inside of that simulated system. And then that simulated environment is then replicated at the terminals of the device with our hardware under test. So this gives a lot of the flexibility of the purely simulated scenario with also capturing those highly nonlinear dynamics that we can catch in the pure hardware setups. So in general, there tend to be two flavors depending on what is represented in hardware. There's controller hardware in the loop where you're simulating everything outside of the controller board. And then there's power hardware in the loop, or PHIL, where you're simulating everything outside the point of common coupling of that device under test. So for the rest of the talk, I'll be focusing on PHIL applications of these grid-forming inverters. So to provide a little closer look at how PHIL is set up, we have a very common setup that we use here at SANDIA to evaluate grid-forming inverters in hardware in the loop. So at the top, we have our power system that's represented in simulation. And this simulation is running on some real-time environment. In our case, we typically utilize an OpenRT system, although there are a number of other different systems that we can use. And on the bottom, we have our setup in the laboratory where we have some DC side source that's connected to our grid forming inverter as our device under test. The AC side of the grid forming inverter is then connected to a grid simulator and it's operated as an AC amplifier. So the first step in representing this device under test in the lab is in the simulated power system, we want to represent it at whatever node we want. I've labeled that here as node A. So then we create a digital twin in the simulation that represents the hardware that we have in the lab. And this digital twin is typically some sort of source, and it can either be a voltage source or a current source, depending on the specifics of the device under test in the power system. So we then control that simulated digital twin via a measured power flow taken in the lab. And if we're representing this device under test as a current source, then we use the measured current flow to control that current source in the simulation. They then use the measurement taken from the point of common coupling inside of simulation to control the output of our AC simulator in the lab. And then that gives us our closed loop interaction between hardware and simulation that we use to carry out our hardware and loop evaluation. So this implementation where we have this digital twin that's represented as a current source in simulation and it's fed by a measured physical current is typically known as the ideal transformer method. And it's been used relatively extensively to evaluate grid following inverters, among other types of device under test. So this here is an example of an HIL evaluation we did for PNM, which is the local utility, for a relatively long feeder with significant PV at the ends of the feeder. During periods of high insulation, there would be high overvoltage events on the feeder, and that would result in overvoltage events due to the power injection from the PV arrays at the end of these long lines. So we utilized hardware in the loop of these small collections of microinverters to emulate the behavior of these multi-megawatt arrays of interest through scaling of our hardware and loop setup. And then we were able to implement different control mechanisms to evaluate how they would mitigate these overvoltage and regulation impacts on these long feeders. So this method works very well for grid following inverters. It's very stable, and you can easily represent very, very large systems through scaling. But the question is, how applicable is this general HIL mechanism to grid forming inverters? We know it works for grid following. How well does it work for grid forming? So for that answer to the question, we actually have to dive a little deeper into how the PHIL process works, especially for this most common method, which is the ideal transformer method. So there's several other methods of implementation, but we like the ideal transformer method here at SANDIA because it's really simple to implement. It's simple to implement in the lab. It's simple to implement in simulation. It has a very, very fast solve time, and it has fairly good numerical stability compared to some of these other methods. So at the top here, I show a schematic of how the ideal transformer method works. On the left, in simulation, you have a system with some sort of digital twin representation of your real device. So that's all in simulation. On the right side, you have the representation of what you have in the laboratory. So it's some physical device under test that's connected to a device that's connected to an AC amplifier. And this device under test has some sort of characteristic impedance, Z DUT, that's associated with it. So to couple the simulation and the laboratory experiment and close that loop, you really have to go through a number of different steps, each of which can induce error or instability in your final experiment. So be very, very careful in how you actually implement these. So starting on the left in simulation, you have to measure that voltage at the interconnection. You then scale this, carry out a digital analog conversion, scale it again, and then use that voltage signal in order to control your amplifier. On the reverse direction for that loop, you're measuring the current flow that's injected into your device under test. You're scaling it, going through an analog to digital conversion, and then injecting that to control the current source that you have inside of your simulation. So this is all great, and it works well for a wide variety of applications, but there is a problem. So the ideal transformer method is technically trying to represent the impedance of a device under test, but a grid forming inverter is not a pure impedance, but is actually a 4-quadrant voltage source. And as any first-year electrical engineer can tell you, when you have two directly connected voltage sources together, you can run into problems. And at best, this setup tends to be metastable, and it can really result in pretty significant instabilities under dynamic and transient conditions because you have this grid-forming inverter, which is trying to regulate voltage, and an AC amplifier, which is trying to regulate voltage, and they're directly connected together. So, the first-year electrical engineering student is saying to themselves, well, why don't you just represent the grid-forming inverter as a voltage source and then operate the amplifier as a current source? And this is actually a totally viable solution. But historically, most grid simulators and AC amplifiers have been voltage sources. There are AC amplifiers that you can operate in this current control mode, and this is especially true for some of the newer units in the market. But at Sandia, we tend to stick with these voltage source amplifiers for a couple different reasons. The first is historical. We started off as a PV inverter testing facility, so most of our experience and our available equipment are these amplifiers that operate in a voltage control mode. And that tends to be true in a lot of different laboratories that you'll find across the country and across the world. Secondly, amplifiers really, most of the amplifiers on the market can't change between this voltage mode and this current control mode without having a restart. So certain hybrid operational scenarios where you have grid forming inverters and grid following inverters, they can be really tricky if you need to switch between this voltage control mode and this current control mode. So really tend to keep everything as a voltage source and then try to deal with these instabilities as we come to them. And finally, operating in a current control mode really doesn't mean that it's intrinsically stable. It doesn't eliminate all the stability problems of grid forming inverters and hardware loop just because it's being operated in a current source. It's still a voltage source converter that's being operated in a current control mode, and you can get instabilities during testing. So you still have to be very, very careful when evaluating grid forming inverters in these hardware and loops, and you'll come up with some of the same problems that you're using for these voltage control amplifiers. So this is an example of a waveform that you can get if you're operating a grid forming inverter with a voltage source amplifier. And as you can see, it looks really, really terrible. And I've, of course, cherry picked some of the really, really bad examples of a highly distorted waveform here. This is from a low inertia system, so you really don't have a firm bus to dampen out any of these oscillations. But you could see that there's both significant noise in the high frequency regime on the lower right, as well as low frequency oscillations, where you get this grid forming inverter oscillating with the power system in the low frequency regime on the upper left. So you get this high frequency noise that has a number of different components to it. You can get it from electromagnetic coupling in the laboratory, you can get error injection from your physical sensors, and you can get quantification error from the analog to digital conversion. At the low frequency regime, in simulation, you really have to account for all of these inductive parasitics that are present in the lab and represent those in the power system as well, or else you'll get these low frequency oscillations. And you also have to be very, very, very sure that you have complete calibration of the AC amplifier and it's correct in both voltage magnitude as well as phase angle in order to account for some of the time periods that take this analog to digital conversion and the scaling with the time scale of the real-time simulation so that you can account for that in hardware. But even with a waveform such as this, that's really, really noisy, that's really, really bad, you can get a simulation and you can get it to run. And it works okay, especially if you're just looking at things in the steady state. But where you really run into problems is with transient stability. But even without taking any kind of broad precautions, you can still get some moderate results with grid forming inverters just at the steady state if you don't take into account these transients. But we'd really like to improve the stability for these transient conditions and really make sure that our waveforms don't look this ugly. Especially if we want to look at dynamic systems. If you have a waveform like I showed before, you really are going to move into an instability regime really, really quickly, and you're not going to be able to evaluate all the dynamic scenarios that we're interested in because your poles are going to be so close to the wrong plane. So one of the key things that you can do is appropriate filtering of the waveform to eliminate some of these aspects of noise that are injected either in your hardware setup due to parasitics or injected at the high frequency end due to things like electromagnetic coupling. You know, of course, the choice of filtering and the type of filtering that you use is really a Goldilocks proposition. So having a really, really tight filter to filter out both the high frequency and low frequency components can really improve your experimental stability. but it tends to reduce the fidelity of the system you have by removing oscillation modes that might actually be present in the system. So the real key is to have a filter that's as permissive as possible while you can still kind of maintain this experimental transient stability and have the minimum amount of filtering that you can get away with and still impose stability. So typically in our grid following hardware and loop experiments, we utilize a low pass filter. And this will accurately filter out most of the high frequency noise in the system that can really introduce instabilities when you're doing different transient scenarios, while leaving a lot of the low frequency modes and the oscillation that might be there in the power system relatively intact. So the advantages of the low pass filter is that it's a really simple filter. It works really well. It has a very low computational burden, and it's proven to be very robust in a wide variety of applications, especially in grid following applications. But the problem with the low pass filter, and you might have to think back to your intro circuits class, is that the transfer function of a low pass filter will lead to a phase shift at just about every frequency. And this manifests itself in hardware and loop in a false injection of reactive power. If you are shifting that voltage or current waveform, that results in a reactive power injection. That's actually a false reactive power injection. So if you have a false reactive power injection, that of course can lead to inaccuracies and doesn't really replicate what's happening in real life. So when you use a low pass filter, that requires some sort of correction for this phase angle shift, and what we use is called a lead compensator. And this lead compensator is a transfer function that corrects the phase angle shift due to the low pass filter, and then it eliminates this false injection of reactive power. So this filtering followed by a lead compensator has really been shown to be very reliable for grid following inverters, and it keeps all of those transfer functions on the left-hand side where they belong so that you can have lots of dynamic transient scenarios and maintain stability. So we've got our filtering mechanism in place. We've shown that it works well with grid following inverters, and we're ready to try it on a grid forming inverter. So this is the result of one of our first hardware and loop attempts with a grid forming inverter. In the lab, we have a 100 kilowatt grid forming inverter. It's operating in PQ mode, and it's integrated into our hardware and loop setup. In the simulation is a microgrid system that has a load of around 500 kilowatts and a simulated 600 kilowatt diesel generator. So at the start of the simulation, we command a power output of 20 kilowatts from the grid forming inverter. And since we want to emulate a larger system than what we have in the lab, we start to increase that scaling factor for the current injection inside of our simulation so we can accurately replicate much larger systems. And we're stepping it, and these are the numbers at around 400 kilowatts from 1 to 2 to 3, et cetera, to try to replicate that larger system. So you can see that as we step up our current scaling we increase the power injected in that simulation from the grid forming inverter in mauve, and that has a similar decrease in the power injection from our simulated diesel in cyan. However, when we get to a scale factor of 7, we hit an instability, and our HIL experiment goes unstable. We get an undamped oscillation of power that flows between that grid forming inverter and that inverter. So luckily, both the grid forming inverter and the amplifier, our power electronic devices, they both tripped offline before any real damage can be done, but it's still an uncontrolled oscillation of power that quickly scales out of control. And you could see, if we zoom in here, that we have these oscillations in the system. And when we command a scale factor of 7, that's enough just to push it into the wrong plane, and we have this exponential increase in that oscillation back and forth in between the simulation, so that quickly results in an instability. So the question is, what do we do? Well, the solution that we eventually landed on was doing away with our low pass filter, because a low pass filter with a lead compensator does not necessarily guarantee stability for grid forming inverters. And the problem is that the low pass filter doesn't really filter out all of those harmonic components that I mentioned, both at the high frequency regime as well as the low frequency regime. So we were using a first order low pass filter. First, we tried a second order low pass filter, but that actually yields greater instabilities. So the solution that we came to was moving from a first order low pass filter to a second order band pass filter that's centered around 60 hertz. And this will tend to shift the poles back to left-hand plane, but it does require some fine tuning to maintain stability. But the really nice thing about the band pass filter compared to the low pass filter is that there is no phase delay around the center frequency, or 60 hertz. So you get no false injection of reactive power, and therefore no lead compensation is required, which makes those simulations simpler and a lot more stable than having this low pass filter, which shifts the phase angle that then requires correction. So armed with our tuned band pass filter, we tried again in this scenario where we have our grid form inverter injecting 20 kilowatts in PQ mode, and then we scale that system to represent a much larger system. And as you can see here, we start scaling up our system. We get injected power up to over 400 kilowatts with a current scaling of over 10. That replicates in a reduction in the simulated genset power injection, and we maintain our stability all the way up to an injection factor of 10, which represents a 1 megawatt system. So, of course, in this specific example, we've filtered the waveform really to ensure stability under these dynamic conditions at the possible cost of some of the fidelity. We've used a band pass filter. We filtered out some of that high frequency noise, some of that low frequency noise. So there really is some art to this. And of course, you can begin to add back in some of that pre-filter noise if you believe it's an accurate representation of the system. So what we tend to do is this. If we want to scale a grid forming inverter by a factor of n, we use this band pass filter to filter the waveform. We then scale it by a factor of n-1 and add back in that original waveform with that noise to get a factor of n. So then we're adding back in some of that original waveform if we think it's an accurate representation. So you have some freedom to do this based on different scaling factors, where you have a scaling factor for the original waveform, as well as a scaling factor for the filtered waveform that you can then combine for your end use scaling factor that has some balance between stability and fidelity of the system. So for the rest of the presentation, I wanted to give you some use case examples of this hardware and loop experiments that we've carried out with grid forming inverters that I think highlight some of this flexibility and some of the challenges of evaluating grid forming inverters in hardware and loop. So a few years ago, we participated in a project with the Alaska Center for Energy and Power, ACEP, and the Alaska Village Electric Cooperative, or AVEC, to try to understand the hardware and control methods that were necessary for utilizing an energy storage-backed grid forming inverter for spinning reserve for the purposes of displacing diesel fuel in an islanded microgrid system. So we called this system a grid bridge system, or a GBS. And we were looking at this through hardware and loop of a rural islanded electrical system. So the village of St. Mary's is around 500 kilowatts and historically has been supplied diesel fuel up the Yukon River to supply a bank of 3 diesel generators that were used to supply power to the village. However, the Yukon River, where St. Mary's is located, is impassable from the months of about August to April, which precludes new shipments for arriving for about 9 months out of the year. So there's this really drastic need for high reliability, low maintenance components that can reduce the need for diesel fuel in these villages. And since the energy costs tend to be high due to the large shipment of diesel fuel, there's really this opportunity for technologies that might not be economical in other environments or other power systems. So in order to decrease the operational costs and increase reliability, AVEC has been looking at a three-part plan for St. Mary's. Part one of increasing reliability and decreasing costs was the installation of a 900 kilowatt Type 4 wind turbine generator that was connected directly to St. Mary's. This wind turbine officially went online in 2019, and it really instantly increased the penetration of renewables to over 100% in the St. Mary's system. So while this saves significant diesel fuel through production of bulk energy, it does require a relatively large spinning reserve since that wind power is non-firm. So you have to make up for it by having a large amount of spinning reserve in the diesels. So usually this would be taken care of by idling a generator or multiple generators at its minimum loading, which unfortunately utilizes fuel. You can get a further reduction of fuel by taking that spinning reserve requirement off the diesel generators and instead putting on energy storage, which has relatively little power requirement when it's quiescent, and you can only inject power when you need it. So this is a look at our simulated St. Mary's system. We have a grid forming inverter and energy storage unit in hardware, with the rest of the unit being in simulation. I've denoted the portion that's in hardware in green here. And we're scaling our 100 kilowatt grid forming inverter to emulate a 1 megawatt system. In the St. Mary's system, there's a variety of single and three-phase loads, and the power is generated by a simulated bank of 3 diesel generators, as well as a simulated wind turbine, although we do have the option of putting these in hardware in the loop, since that hardware does exist in the lab. But we're looking at a contingency here where we have an instantaneous drop of wind that results in the wind penetration for the system going from 85% down to 15% in about 2 seconds, which requires really fast injection of power from the other generator assets in order to keep the frequency of the system within bounds. So we were evaluating how the grid forming inverter can improve power quality of the system and then reduce these deviations in frequency and voltage, and also reduce the time period of this generator response in order to save fuel. So first, we're going to take a look at the response of the system to this reduction in wind scenario without the grid bridge system, so with no grid forming inverter in the system. And you can see the power profile at the top. There's a decrease in wind power, which is the purple trace. And when there's this decrease in wind power, we have the simulated diesel generator output in blue make up for that to keep the power relatively stable. So below that power profile, you could see the frequency and the voltage deviations that are associated with the loss of wind scenario for 1 generator, 2 generators, and 3 generators that are online and able to provide power. So you could see there's relatively large frequency deviations for the single generator case in blue, and you can actually have frequency deviations to below around 58 hertz. And although, a single generator, a single genset unit can supply the bulk power needs, it can ensure that your frequency and your voltage remain in bounds. So that means that you'll need 2 or even 3 generators to abate the frequency and voltage deviations under this type of wind contingency events. So you can compare this to when we have the grid forming inverter in the system. And during that event, you can see a large injection of power of the grid bridge system in red, injects power very, very fast and then trails off over time as that diesel genset sort of ramps up quite slowly. And you could see the impact that the grid forming inverter has on the time scale of the diesel genset. With no grid forming inverter in the system, you get this very, very fast response as the diesel genset ramps up as quickly as possible in order to abate those frequency deviations. With the grid bridge system, it allows that diesel genset to come to the output power much more slowly. And this slow dynamics of the system also saves a non-trivial amount of fuel, regardless of the number of generators in the system. So the results of once you have a grid bridge system supplying the spinning reserve for the system is that you get much smaller frequency deviations when you have this grid bridge system. So with a single generator and the grid forming inverter in blue, you get much better frequency response than you got even with the bank of 3 generators because of this quick injection of power due to the grid forming inverter. And for this system, we found that you can get upwards of around an 87% improvement on the frequency deviation due to the presence of this grid forming inverter. So if you have a grid forming inverter, you only need the single generator plus the grid forming unit, the grid bridge system, in order to supply all of that remaining load as well as the spinning reserve for the system. So that saves significant amount of fuel because you don't have to idle that second and the third generator. And additionally, it slows down the time period of response of that single generator. So you actually save a non-trivial amount of fuel due to the slower dynamics of the system. So one of the advantages for hardware in loop is that you have this ability to apply conditions that are difficult, if not outright impossible to apply in the field. So things like fault behavior. And one of these tests is the classic phase jump test. So the phase jump test comes out of an event that occurred in 2016 known as the Blue Cut Fire. So basically in California, there was a fire and a fault in this electrical system of that caused by that fire caused a discontinuity in the voltage phase. And this is known as a phase jump. So all of the grid following inverters on that system saw this discontinuity in the voltage and then registered this phase jump as a frequency droop and totally tripped offline. So in this event, that was the cause of around 1.2 gigawatts of PV to trip offline and further exacerbated some of the problems in the system, even though there really was no deviation in frequency in the system. So in 2018, 1547 was amended to require this new behavior and testing for this phase jump event so that inverters could ride through these types of phase jumps and not trip offline. So you can evaluate a phase jump test in hardware through an emulated fault or some of the newer grid simulators actually have these newer test protocols programmed into them. But we really like to keep it simple, and we utilize our real-time simulator in order to control our voltage amplifier and institute these tests. So it's actually a hardware in-loop test that we run in a phase jump manner. So these tests are pretty standard, but we are interested in applying them to grid forming inverters to kind of compare their behavior with grid following inverters. So here are the results for a 15-degree phase jump for a grid following inverter on the left and a grid forming inverter on the right. And that grid forming inverter is in PQ mode. We have 3 different traces here. At the top is the RMS current for the 3 phases. In the middle is the symmetrical current, the positive, negative, and 0 sequence currents. And at the bottom, we have the active and the reactive powers per phase of the system. So, just on first blush, you can see totally different behaviors from the grid following and the grid forming device. So if we look at that the grid following inverter, so obviously we can see that it oscillates around this nominal power value and looks to be some sort of hysteresis type control mechanism that as it rides through this phase jump. And you can get current swings and power swings of this grid following inverter around 50%. The current values are all roughly symmetrical across the phases, and then the device returns to its pre-fault conditions in about a quarter second after that fault is cleared. Also, from the middle graph, as you would expect for a grid following inverter, it is supplying almost entirely positive sequence current, and you have little to no sequencing or sourcing of 0 or negative sequence values. So you can compare this to the grid forming inverter that we have on the right. So first, you can see a breaking of symmetry between the phases. We have the phase B current that increases significantly. The grid forming inverter is also significantly faster to return to its pre-fault state, and it returns that pre-fault state in about 1/10 of a second, rather than a quarter of a second. Although it isn't completely its pre-fault state, because if you notice, after it rides through that fault and returns to its equilibrium condition, there is a slight oscillation after the ride-through event that isn't present in that pre-fault event. Also, unlike the grid following inverter, the grid forming inverter is able to provide positive, negative, and zero sequence current throughout that event. However, the positive sequence also shows this oscillatory behavior that doesn't quite die out once it returns to its pre-fault state. And finally, the grid forming inverter is able to independently control the phase power throughout the ride through. So not only does it have asymmetry between the phases, but the phase C is actually sinking active power while phase A and B are sourcing active power. So we can see completely different responses and behaviors between these different units, which is really important for designing the selective protection system. And luckily, hardware on loop is a really great tool for evaluating the behavior of these hybrid systems to integrate things like not just the generation units, but controllers, protection equipment, and other hybrid resources, power electronic assets, rotating machines, et cetera. And I'll discuss one of these hybrid hardware in the loop setups next. So this is a project that we worked on last year that was in partnership with EPRI and SNC that was meant to evaluate multi-microgrid controller interactions in hardware in the loop. So our simulated system is a single feeder of the Banshee model, which is a standardized simulation model that's commonly used to evaluate microgrid controllers. And we've altered this model a little bit to incorporate hardware in the loop. So in hardware on one bus, we have a node that has a diesel generator, a grid following inverter, and a resistive load bank. And that's in hardware, so I've marked it in green. We also have a second node here that's independent from the first in hardware that's composed of a grid following inverter, a grid forming inverter, and a resistive inductive load bank. So we have two independent sources of hardware that can operate in a grid connected mode, in a single microgrid islanded mode, or then split into two different microgrids, as I've kind of denoted here. So we were evaluating the behavior of real controllers, real hardware in the lab to reliably control these individual microgrids independently, as well as to coordinate the microgrids to either combine them into a grid connected or islanded mode, or then disassociate them and operate as their individual microgrids. So these controllers are able to communicate to each other via IP TCP, as well as all of the assets and all of the protection elements, both in simulation as well as hardware via Modbus. So we're incorporating not just the analog voltage and current signals that are coming out of the simulation to the generational assets, but also the communications that are going into and out of the simulation that is incorporating both the simulated units as well as the actual hardware units in this case. So there's a lot of communication data streams, as you can imagine. There are hundreds of data streams going into and out of this simulation. So a relatively large computational burden for this sort of experiment. So we've got our two microgrids, and their point of interconnect is being controlled by this protection relay number 106. So we could simulate this protection element like we did for the other breakers throughout the system. But since it's the interconnection between real and actual hardware in the lab, this makes me a little bit nervous, since we could easily damage our test equipment if the simulation had a little bit of a hiccup. I mentioned how it has a relatively high computational burden because of all this communication and the size of the system. Just a little bit of hiccup with the synchronization or the protection elements, and you could really start to damage things in the lab. So in order to kind of mitigate that risk, as well as just add a little bit of a degree of difficulty, we decided to add one more piece of hardware into this hardware in loop simulation. So we have an actual protection unit that's controlling the point of interconnect between these microgrids. And there's two ways that you could actually implement this protection element into the hardware in loop setup. The first is that you can have sources on either side of that protection element, and you can actually flow power in the lab where that protection element is reading that power as it's flowing and controlled by the simulation, sort of another hardware and loop aspect. The other way to do it is to actually emulate the signals of the CTs and the PTs directly from simulation via analog signaling. So this is the path that we actually took, where we were emulating the CT and the PT low voltage signals and exporting that directly from the simulation. So this does require a little bit of calibration to get the scaling, as well as to take into account any of the transfer functions that may be induced by the physical CTs and PTs that are associated with this protection element. So in the full hardware and loop experiment, we have our simulated system, we have 2 nodes of hardware, we have 2 controllers in hardware, and we have our protection element in hardware. So that's a lot of hardware units, and we also have both analog as well as communication signals into and out of the simulation. So these are some of the results from an event where we take the microgrids up from a Blackstart. We Blackstart first the individual microgrids. We then synchronize those 2 microgrids together. After running them as a combined island for a little while, we then disassociate those 2 microgrids. So the data shown here is from the hardware controllers that's collected via Modbus communications with both those simulated as well as those real assets. So it's a little bit choppy due to the 1-second update rate. But what you can see on the left is the frequency versus time. And it's the frequency on both sides of that synchronization breaker 106. When the switch is off, we see the frequency components of both sides that don't match each other. When we synchronize those 2 microgrids, which is shown by the red trace when CB106 is on, those frequencies move perfectly in step. Turn the breaker off again in hardware, and then in simulation, those frequencies disassociate again. So we're pretty sure that we have electrical communication between these 2 different microgrids. On the right side are the voltage traces on either side of that switch. And you can see us bring up the voltage on both sides from the blue and the green traces when we Blackstart these microgrids individually. The red trace again indicates what that synchronizing switch state is. So the voltages on either side of that circuit breaker track each other exactly when we connect these microgrids together, and then they separate when we disassociate those 2 microgrids into 2 independently operating microgrids. But since we have this real unit in hardware, we can actually see the waveform data from the association and the dissociation of the microgrids. So on the top, you can see the voltage trace in blue and in red on both sides of that breaker, with the breaker state in black. On the bottom is the current through that breaker, with the black being the current state. So when we connect the microgrids, we initiate a 25A reclosure on the relay, which ensures that the voltage magnitude, the frequency, and the voltage phase angle are all within our prescribed limits. For these tests, since we had a lot of hardware, we used a relatively small window. So it was a 5-degree phase angle as our limits. But when we initiate synchronization, you can see we have almost no deviation in the voltage waveform. And because of that, very little inrush current between the 2 microgrids, which is really good for a hardware under test. Again, that you can see from the current traces on the bottom that we do have some oscillations in this system due to interactions between the simulated and the hardware assets, as well as the interactions between these 2 different microgrids, since it's a low inertia system. Although the oscillations are relatively minor and they don't grow in time, so they really don't affect our system stability as we carry out these hardware and loop simulations. So with both of the microgrids combined, we carried out some load step changes, which is why you see some of the chop in the current trace in red when that switch is closed. We just wanted to associate a dynamic condition with that. And then when we open the switch, again, we see really no transient either in the voltage or the current profile during that switch opening. So this was a project where we could evaluate generation, control, and protection elements all operating together in this dynamic environment in hardware in the loop. So it really illustrates some of the flexibility that hardware in the loop has. So for the final example case, I wanted to touch on something that I think is by far the trickiest thing that you can do in hardware and loop evaluation for grid forming inverters, and that's Blackstart. So let's say in simulation, we have some system that we want to Blackstart. And I just have a simple system here shown at the top that has a grid forming inverter that's Blackstarting some load, although the problem is generally generalizable to any Blackstart system. But basically, when you close the unenergized system, you instantaneously have voltage at the terminals of the grid forming inverter that wants to be at 1 PU, and you're telling the voltage amplifier that it should have 0 voltage in the system. And that's basically the definition of Blackstart. So the problem is that we then have two voltage sources. The grid forming inverter wants the voltage to be at 1 PU. The AC amplifier wants the voltage to be at 0 PU, and they're fighting against each other. So you get very, very, very bad system instability. And as a side note, you'll also get the same condition if you try to connect a grid forming inverter that only operates in an asynchronous mode and doesn't have some sort of droop functionality. You'll get this instability with the AC amplifier, regardless of the voltage in that case, even if they're both at 1 PU. So this is actually a really difficult problem. And there are a number of ways that you can go about solving it. So the solution that I'm going to discuss involves physically decoupling the power amplifier from the grid forming inverter through the use of a physical inductor. So basically you have an inductor that you place between the device under test and the AC amplifier. And then that inductor, which with its accompanying parasitics, is then replicated exactly in simulation in a digital twin configuration. So then you measure the voltage at the input side of the inductor in hardware, and you inject that into the simulation. And then you measure the voltage out of the simulated inductor and use that to control your power amplifier. So this is slightly different than the ideal transformer method that I discussed previously, because it's both an input and an output voltage waveform, whereas the ideal transformer method is always a voltage and a current waveform pair. And whether it's input or output depends on how you're exactly running it, but it's always a voltage and a current. So for this kind of test, we want to define our stability limits as well as the accuracy of the system in terms of its capacity to maintain trackability between the current flow in hardware, I sub I, and the current flow in simulation, I sub S. So we have to consider the pathways and the transformations that those signals are going through. And I've listed here a Laplace transform, a Laplace block diagram that links the transfer functions from the hardware and from the simulation side. The black pathway is the transfer function that we see in hardware, while the blue pathway is in simulation. On the hardware side, our voltage transformation only occurs through that simple transformation, U of S, which is represented by that physical inductor. So it's composed of some inductance as well as some series resistance. On the simulation side in blue, our voltage, it first goes through a filter. In this case, we're using a low pass filter. So that's H sub LP, and then that's followed by the lead compensator F sub L. This is in series with a function T of S that represents the intrinsic impedance of the system in simulation Z sub L. So that system that we're trying to replicate has some characteristic impedance, and that T of S represents that. So in order for this system to be stable, the output signal I sub I has to respond to the input signal V sub I in a bounded manner. So it can't go to infinity. And we can derive a transfer function between these two quantities, I sub I and V sub I, which I've defined here. So to ensure stability, we have to ensure that there are no realistic poles in the system so that the denominators of this equation can't go to 0. So luckily, the cutoff frequency of our filter, the tuning parameter, P sub 1, and the inductor L sub I and the resistance values R sub I are all real positive quantities. So this means that those denominators will not go to zero and that those poles will stay where they belong and ensure stable behavior. So then our stability only becomes determined by that last denominator. L sub S and R sub S, which represent the simulated inductance and the simulated resistance, are real values. So then we really need to calculate the representative system impedance, Z sub L, in order to determine where those poles are and if we have stability. So for a series RLC case, Z sub L can be represented by this equation at the top. And if we substitute this into the previous equation and we solve for all those roots, we get a fairly complex equation for the values of S. So to ensure numerical stability, the numerator has to be less than zero. So after a lot of algebra, we can come up with this inequality that ensures stability for this system. So this inequality relates to the simulated series inductance L sub S and the characteristic impedance of the simulated power system L sub L. As long as these quantities are greater than zero, then the system should always be stable. And since L sub S and L sub L should always be real positive quantities, this method should be exponentially stable for all power systems that can be represented by equivalent series RLC circuit. For the RLC parallel case, it's a little more complicated, and obtaining a closed loop solution is actually relatively difficult. So you have to approach the situation numerically. And you can actually prove that for this method, the tractability, or how accurately the simulated current I sub S tracks the real current I sub I, is really dictated by how well you could represent the real inductor in simulation as a digital twin. The more accurately we can represent this, including any non-idealities or non-linearities, the more accurate those results will be. So in order to validate this method, we've tested on a commercially available split phase grid forming inverter that was interfaced with our voltage source power amplifier. And you can see a schematic here of the hardware that's in black, as well as the simulated system that's in blue. So this particular inverter does not provide droop control capabilities, so the inverter is only in isochronous mode. And we wanted to use it to Blackstart a simulated system that has a characteristic impedance Z sub L. So we ran these tests with a Z sub L that was provided both by our simulated system as well as in reality with a load bank. So on the right, we have plots of the real and reactive powers provided by the grid forming inverter. And we've measured this power in simulation, which is P sub S in red, in hardware with a power amplifier, which is P sub H in blue, and then in a pure hardware setup with a load bank, and that's the yellow trace. And then we take abrupt changes in Z sub L in this stepwise fashion to demonstrate that we can maintain stability under these dynamic conditions. So we can see that the results of the P-HIL experiments match those results that we're getting from the physical impedance load bank with an accuracy of around 5%. In this case, the power factor is close to unity because we're using mostly resistive loads, but there's a slight mismatch in the amount of reactive power in the methods, since we don't fully account for some of the additional reactance that's being injected by the grid forming inverter due to the LC output filter of the grid forming inverter. And here we have traces of current, voltage, and frequency of the grid forming inverter when it's connected either straight into the load bank or through our power amplifier in these Blackstart conditions. So we get excellent agreement in all three of these metrics that show the tractability between this pure hardware as well as the P-HIL for this Blackstart method. So while these results are specifically for this relatively simple system that we could replicate with our load bank purely in hardware, it's also generally applicable to many simulated systems that can be represented by some characteristic impedance Z sub L. So this method with physical inductors and the digital twins is only one of a couple different methods for evaluating the Blackstart of inverters. And there's several other ones that we're considering that don't require the actual implementation of physical hardware. So while we have some good results in simulation for some of those methods, we're currently working on actually applying those in a full hardware as well as PHIL tests. So it's really a work in progress. Okay, so in summary, I hope that I've shown you that hardware in loop is a really flexible technique that strikes this good balance between experimental flexibility and accuracy. It's been used for a wide variety of applications, but applying to grid forming inverters specifically is not necessarily straightforward. So you really have to be careful because you can easily run into these instability issues due to interactions between the grid forming inverter and the grid simulator, since it's a voltage source device. So we've utilized filtering in order to control these signals and ensure the transient stability during these dynamic testing conditions, but there are lots of other things that you can do in order to ensure stability. I've also gone over a few use cases for these grid forming inverters and power hardware in loop. So we've demonstrated grid forming inverters for spinning reserve and a microgrid system, and showing those interactions with larger banks of diesel gensets. I've also described phase jump testing, which allows us to apply faults to grid forming inverters and compare those results to some of the same tests that we're running with grid following inverters. And I've described some of our hybrid testing capabilities where we have protection, power assets, and control all in the same experiment. And finally, I've described one of our methods that we use for initiating Blackstart in hardware and loop for grid forming inverters. So that's all I have for today, and I wanted to thank everyone for their time and for their attention, as well as Ben and the rest of the UNIFI team for giving me the opportunity to present some of our work on hardware and loop for grid forming inverters. So thank you very much.
Okay, Jack, thank you. So we'll go ahead and stop our recording.